Hello, my name is Lauren Mack, and this is my analysis of Lab 2 Projectile Motion. The purpose of this lab is to analyze an object's actual change in y position over time using a software called Tracker and compare that with its predicted change in position with and without drag in a model called GlowScript. We then use the two models to compare how drag force affects the actual change in an object's motion. What we see as a result is that the computational model without drag is expected to have different y values than the actual model due to the interaction of the drag force. In our experiment, what we did was we recorded a paper ball being thrown at an initial height of slightly under 1 meter. We then uploaded a video to Tracker and found that the incremental change in y position, and we did this by tracking snapshots of the object's motion as seen as the picture. We then used the initial time, the change in time, the initial position, the final position in both the x and y directions to find the initial velocity. After this, we used the initial velocity to create a GlowScript computational model without drag and with drag. All three models, without drag, with drag, and the actual tracker model were compared graphically. The principles used in this lab include Newton's second law, which states that there is a direct relationship between the change in momentum over the change in time with to the magnitude of net force, which we can then use to derive the velocity update equation, and thus the position update formula. Some new equations that we have in this lab include drag, which is a resistive force to an object's downward motion. We also have gravitational force, which is the direction of an object's downward motion, which is in the direction of an object's downward motion. And from these two ideas, we can explain the concept of terminal velocity, which states that the following object must have air resistance that is equal to the magnitude of gravity, which then creates a zero net force and a constant velocity moving downwards. So the system that we have is a paper ball, and the surroundings include everything outside of it. In this case, it would be air resistance and the force of gravity from the Earth on the ball. We then found the initial velocity by taking the change in x direction over the change in time. We plug the initial velocity into GlowScript as well as the initial position found in the tracker, and we get these graphs, one with drag and the other without drag. And as you can see in the models, the graph tracking the drag with drag has a much flatter graph than the one without drag. With the initial conditions, we set the ball position to the initial height in meters, the ball's velocity in the x direction since we threw the ball with an initial velocity in the x direction. We also charted the initial time, which I changed in my graphing model because the change in time is more important than the actual values of time. And without drag force, we have 0 for the B proportionality constant, which causes the force of drag to be equal to 0. In the model with drag, we changed the proportionality constant to 0.000258 due to the fact that this was an estimated value that created values closest to the actual change in position found in Tracker. This, in relation to the F-drag equation modeled in GlowScript, created a new component in FNet that slowed the ball's downward motion. As you can see in the graphs, the blue values detail that the change in y with drag found in GlowScript overlap with the actual change found in Tracker, represented by the orange values. The green values show that the GlowScript model without drag under approximate the actual values found in Tracker, signifying that drag is a component affecting the object's actual motion. The possible errors include inconsistencies when choosing points on Tracker, errors when calculating the initial velocity, and when choosing a B value. Since it was purely up to estimation, there could have been closer B values that reflected a more accurate drag GlowScript model to the actual change in the object's motion. So, does the computational model predict terminal velocity? The model with drag predicts terminal velocity in the near future due to the fact that the velocity in the y direction over time is approaching 0 net change, indicating 0 acceleration and thus 0 net force. And what if the ball was thrown upwards at the same initial velocity? The time in the air would be longer due to the larger component of velocity being in that direction. In conclusion, drag force creates a noticeable difference between the actual data and the computational data, and potential errors in calculation and measurement can prevent precision in data. Thank you.